Hello, everyone. In this session, I'm going to talk about code contracts verification using Microsoft .NET code contract library, which is part of .NET. So no need to install any tools. As you can see here, it's basically using system package from the Microsoft .NET distribution. Okay, so I will spend a few minutes quickly explaining the goal of this problem. The goal of this problem is to find an issue in this piece of code statically without running the code. Okay, so in theory of computing, we have notion of formal specification, which may come across a bit strange if you're a beginner. But these days, lots of interesting tools have been developed. You can specify the contract using the programming language itself instead of using some Greek notations. Okay, for example, here, the program is supposed to compute the absolute value of a given number I, right? So the program is making a claim that that's basically the contract, that it will ensure the result will be greater than or equal to 0. So absolute value by its definition means that, right, that the output is always greater than or equal to 0. Okay. So where is the program? The program itself is one-liner here, right? It takes the number I, it checks whether I is greater than 0. If it is greater than 0, it returns I because the input itself is already non-negative. Otherwise, it puts a minus in the front. So, for example, if you send in -2, the output will be 2. If you send in -50, the output will be 50. If you send in 25, the output will be 25. Okay, that's basically the purpose of the absolute function. However, we don't really know whether that's the case for all possible I, right? I just played with 3 input I's and then I say, okay, now I'm done. But what happens if there are some special corner cases where this can fail? So let's see whether the tool can verify this, right? This is the claim the programmer is making about the absolute function. Let's see whether we can run it and see what happens. Okay, Microsoft tool is giving us some warning. It says that the contract suggested requires, the contract is possibly wrong for min value, right? The possible negation of min value at line number 12. And therefore, they're saying add a suggestion to the code that the input I better be greater than 0 or it's not equal to min value, right? That's basically what they're saying. So as long as this contract that requires is added as part of the code, that particular code is correct. So let me explain why the min value is a problem. In my other video series, I explained about integer arithmetic in general, but very quickly, say your number I is just a 3-bit number, right? Just to make it easier for us to draw. So what happens if you have a 3-bit number? A 3-bit number has this box, right? 3 bits are only allowed, right? Okay, so this is the sign. This bit is a special bit, right? For an integer type, this is an integer type. So this must be used for sign. This is called the sign bit. Sign bit, if it is 1, this means this number is less than 0. Otherwise, this number is greater than 0. Okay, this is the meaning of this sign bit. The sign bit decides whether the number I is less than 0 or greater than or equal to 0, right? Okay. So now, what happens if you have, say, a 3-bit number, as we have seen here? A 3-bit number, the maximum value of a 3-bit number, we can draw it quickly on a clock, right? Almost a clock. This is 0. This is 1. We can draw 2. We can have 3. But we can't represent 4 in a 3-bit number, okay? Especially for 2's complement number integer, right? That's what I'm talking about. So 4 becomes actually -4, and then it will be -3, right? And -2 and -1. This is basically the representation for 3-bit representation. Usually integers are 32-bit representations in modern machines, but let's take it simple, right? This is 3-bit. So with 3-bit, as you can see, these are the possible values we can represent. So now consider -4. What happens if you take the absolute value of -4? It is +4, right? But plus 4 requires, how many bits do you need to represent plus 4? Plus 4 means you need 2 power 2, right? 2 power 2 is plus 4. So this is the scenario you need, right? This is 2 power 4. 2 power 0, 2 power 1, 2 power 2. But how many bits do you need here? You need 4 bits. That means in the context when you have only 3 bits, this 0 will go away, right? It has to be thrown out. What you're ending up is basically 1 0 0, which is nothing but minus 4 in 3-bit representation. Therefore, absolute value of minus 4 is basically the same as minus 4, which is quite weird, but that's how computer arithmetic works. Therefore, the program will not work correctly if the input reaches the smallest possible negative value, right? So you have your number line now. Here is your 0, and here is your minus 4, which is the smallest possible negative value. Remember, smallest means you have to go all the way to the left end. So if the input is the smallest possible value, the program fails. That's the reason why this particular tool suggested an invariant, or a contract rather, to add it as part of the absolute specification. So now I will add that and then verify it. Okay. So what is the contract saying? It says contractor requires, right? So contractor requires. It says either the input is greater than or equal to 0. Well, I will skip that. Why do we need that? Maybe we can even simplify. Contract requires that the value is not equal to min value, right? The input I is not equal to the 32-bit representation is what .NET uses, min value. Okay, so now let's verify. Hopefully the program is now proven correct. Okay, it's now proven correct. It says validated 100%. All of the assertions. I'm not going to talk about all the fine-grained details behind where are these 4 assertions coming from. The tool uses some modern mathematics, maybe old mathematics, but applied in a new way to prove correctness of programs. So as you can see here, requires means everybody who's using the absolute function must satisfy this contract. Okay. Then the program guarantees that it will give a value which is greater than or equal to 0. The result is basically what the program is returning here, right? The result is something coming from the return code, and the algorithm verifies formally this is the case. So if you behave nicely by satisfying the line number 7, which says the input I is not the smallest negative value or the min value, then you are guaranteed that the absolute function will work correctly, meaning it will satisfy this particular contract. Okay. The different programming languages and different tools have different syntax for how do you specify the contract, but I find this nice that programmers who are familiar with .NET, for example, can easily specify requires and ensures as part of the programming language and automatically verify when they run programs for all possible inputs. That's basically the idea. There are some limitations, scalability and halting problems and things like that, but in general, small programs that are somewhat non-trivial can be verified already using these kinds of checking tools. All right, in the next segment, I will talk about the other algorithms one by one. Thank you very much. That's all.